Are we ignoring an obvious solution to cabin and cockpit smoke events, like the ones caused by bird strikes and other internal failures? We have now made several videos, both here and on the Mentour Pilot channel, looking at how oil ingested into the compressor stages and the bleed air ducts of the engines can cause smoke to fill up the passenger cabin and cockpit of Boeing 737 MAXes as well as Airbus A320neos. And if that happens, close to the ground especially, it has the potential of increasing pilot workload dramatically at a very critical time of flight. Now, I want to be very clear here. These are quite rare events, and engine and aircraft manufacturers are already busy working on software changes that will make these events much easier for us pilots to handle. But what if there is a better way? Well, Ben and I have discussed this issue while demonstrating it in a simulator, and what we've mentioned almost in passing in those discussions is that there is currently one aircraft that cannot suffer from this particular problem, and that's the Boeing 787. So I will now let Ben explain why that is and what we can learn from it. Over to you, Ben.
Thanks, Petter. And you're absolutely right. The designers of the Boeing 787 took a very unique approach to the way in which air is compressed and then sent to the cabin for air conditioning and pressurization, as well as the various other systems throughout the aircraft. Now, to understand this better, let's first look at how a regular airliner supplies air to the various systems. Now, imagine it's a cold morning and you're a passenger at your nearest major international airport, and in front of you, a massive wide-body airliner is pushing back from the gate and starting engines. Once the engines have started, conditioned air flows through the vents into the cabin and systems quietly come online to protect the wings and the engines from ice. To most people on board, it feels invisible because it's simply part of how flying works. However, all of these systems, the air conditioning, the pressurization, the anti-ice, they all operate from compressed air from the engines. This compressed air is then bled from the engine at certain points of the compressor stages and is then piped throughout the plane. And it's been done this way for decades. The plumbing that makes it all happen has been refined and optimized over time, so it works reliably. And it's so deeply embedded in aircraft design that it simply fades into the background. So what's different about the 787? Well, when Boeing designed this jet, also known as the Dreamliner, they made a decision that quietly broke with that tradition. Instead of trying to refine the plumbing even more, they just removed it, or at least most of it. Boeing decided that the 787 would not rely on engine bleed air to pressurize the cabin, heat the wings, or start its engines. Instead, the aircraft would achieve all of this by using electricity. Lots of electricity. It was a radical choice that reshaped how the 787 works from the inside out, and one that questioned whether or not bleed air is worth it. But the fact that Airbus did not follow Boeing's example and stuck with regular bleed air systems for their newer A350 shows that the answer wasn't exactly conclusive. Now, to understand why all of this matters, let's start with what bleed air actually is and why today every airliner except the 787 depends on it. In a turbofan engine, air is drawn in through the inlet, through the fan, and then the portion of air that's driven through the core is squeezed or compressed through multiple stages of compression before it's eventually sent to the combustion chamber to be mixed with fuel and then ignited. Now, as the air is progressively compressed through the multiple compressor stages, it gets hot, it gets dense, and therefore it's full of energy. And early in the jet age, engineers realized they could tap into that energy to power the aircraft itself. You see, by extracting or bleeding a portion of that air from one or two stages of the engine's compressor, an engine can pressurize and air condition the cabin without needing other complex infrastructure for that particular purpose. Now, after the air is bled from the compressor section, it gets routed to the various systems that depend on it. For example, the bleed air that will air condition and pressurize the aircraft is directed through ducts and vents to something called an air conditioning pack. Now, these packs contain compressors, heat exchangers, and turbines that bring the hot, dense air down to the right temperature and pressure before it gets sent into the cabin. However, as I mentioned earlier, that's not the only thing that engine bleed air is used for. The air that isn't used for air conditioning and pressurization is still super hot, and that hot air is used to heat up the leading edges of the wings and the engine inlets to prevent ice buildup. It can also be used to spin air-driven starters to bring the engines to life and support a variety of secondary pneumatic functions throughout the aircraft. From the design perspective, it's an elegant solution. The engines are already compressing air anyway, so borrowing some of that energy avoids the need for heavy generators, powerful electrical systems, or new technologies. Bleed air made early jetliners simpler, lighter, and easier to certify at a time when electrical power was limited and reliability was one of the top priorities. And that's why bleed air became the standard architecture across the jet age. From early narrow bodies to the long-haul wide bodies, it was proven, it was well understood, and it was dependable. However, there's no such thing as a free lunch, and you're not getting all of that work from the engine for free. In the cruise, bleed air extraction can account for a good percentage of an engine's total fuel burn, depending on how heavily the environmental control system and the anti-ice systems are being used. And that's because despite the improvements made on bleed air systems over the years, they do come with a caveat. Every kilo of air taken from the compressor is air that doesn't get sent to the combustion chamber to be mixed with fuel and then burnt, which effectively robs a bit of power from the engine. Then there's the hardware required to make all of this possible. Bleed air is extremely hot, often well into 200 degrees Celsius, which means that every component that carries it has to survive these extreme temperatures for tens of thousands of flight hours. This requires thick-walled ducting, it requires high-temperature seals, titanium components, insulation blankets, pressure regulators, shut-off valves, and leak detection systems routed throughout the fuselage and wings. Each of these parts adds weight. Each junction adds a potential failure point, and all of it has to be inspected, monitored, and maintained throughout the aircraft's life. Now, before we get into the specifics of the 787, take a look at this. This is Opera, a browser that has made my life a lot easier. Researching an incident used to be a bit of a mess. I was constantly switching between tabs, losing my place, forgetting which document had which detail. But Opera streamlines everything. Let me show you. Opera lets me split my screen into 2, 3, or even 4 ways with a simple drag and drop. So when I'm working, I can have the accident report, flight data, a technical diagram, and my notes all visible at once. And it makes connecting the dots so much easier. And instead of having Google Calendar and Gmail buried in tabs, Opera's sidebar lets me add them right here. With one click, I can access either of those without disrupting my workflow. And I also spent some time customizing the entire look with Opera's themes, and now I have a setup that really feels like it's mine. You can change everything from animated backgrounds to UI colors and even the browser's sounds. But the best feature is Opera AI. It's built right into the browser and is free without an account. So if I want to quickly understand what happened with a certain flight, for example, I just pull up a web page and ask. No need to copy links or upload files, it automatically analyzes the page and gives me a summary. Opera is completely free to download, so you've got nothing to lose, and the link is in the description below. Thanks Opera for sponsoring this video. Now, let's get back to the 787. Now, for decades, the efficiency losses and the complexity of bleed air systems were simply accepted. Fuel was relatively cheap, electrical systems weren't powerful enough to replace pneumatics, and bleed air worked well enough, even if it did have its drawbacks. By the early 2000s though, that balance was beginning to shift. Engines were becoming dramatically more efficient, electrical generation and electronics were advancing quickly, and airlines were demanding step change improvements in fuel burn, maintenance costs, and passenger comfort. And it was around this time that Boeing began designing its first clean sheet airliner of the 21st century and asked, what if the engines didn't need to supply air to the airplane at all, but instead used electricity? The reason they asked this question was because when something in the bleed air system goes wrong, the consequences aren't always trivial. A bleed leak isn't just a nuisance warning light. Hot air escaping where it doesn't belong can damage structure, wiring, or nearby systems. As a result, we pilots treat bleed faults very seriously, And in some cases, a bleed issue can force an aircraft to descend or even divert, even though the engines themselves are working perfectly normally. Again, airliners accepted these limitations for decades because bleed air was familiar and dependable. Maintenance crews understood it, procedures were well established, and the operational cost was simply baked into the economics of flying. However, as fuel prices rose and margins tightened, that inefficiency became harder to ignore. And later on, another issue came into the picture. Because cabin air on traditional airliners is drawn directly from the engines, failures of engine oil seals, even relatively minor ones, can allow traces of oil to enter the bleed air supply, and that's really not good. However, sometimes it's not just traces of oil, but actually several gallons of engine oil, which brings us to the LRD activation that Petter spoke about in the beginning of the video. Now, I'm not going to go into a lot of detail on this system here since Petter already explained it in a previous video, but briefly, the LRD stands for Load Reduction Device. It's a function that several newer engines have to help mitigate the effects of severe engine damage, such as losing a fan blade after a bird strike, for example. Such a blade loss would cause an imbalance in the fan, especially in newer engines that have fewer, wider blades, meaning that each blade represents a bigger percentage of the fan's spinning weight. So, when there is such an imbalance, the LRD system activates and kind of releases the fan section. The LRD does this by enabling the fan to be partially mechanically disconnected from the turbo machinery, and this reduces the severity of the vibration transmitted from the damaged engine to the airframe. However, the release of the fan also releases most of the engine's oil, and much of that oil is then free to move through the compressor stages and make its way to the bleed air system. By that point, the oil is vaporized by the high temperatures and turned into acrid white smoke that becomes incredibly dangerous to breathe. Now, there are software solutions for this. The engines already have vibration sensors which could send a signal to close the bleed valves, stopping this vaporized oil from entering the air conditioning system. But getting rid of the bleed air system altogether would obviously make a much more definitive solution. Now, obviously, jets have had complex electrical systems since the beginning, and each new generation of aircraft relied a little bit more on electricity than the one before it. And this is simply because electrical systems offer a level of precision and control that pneumatic and mechanical systems just can't match. Electrical motors just draw power only when they need it, and electrical loads can be monitored, prioritized, shared, or redistributed instantly. And as solid-state electronics have improved, electrical systems have become lighter and have fewer parts, and are therefore more reliable and far easier to integrate into complex aircraft architectures than sprawling networks of ducts and valves. And eventually, this trend reached a tipping point. Aircraft like the Airbus A320 and the Boeing 777, although still relying heavily on bleed air, featured far more capable electrical systems than anything that came before them. At the same time, engines have become dramatically more efficient. Extremely high bypass turbofans squeeze more thrust from every kilo of fuel, which makes any non-thrust energy extraction, like bleed air, increasingly noticeable. And while fuel and maintenance costs have continued to rise, the cost and weight of electrical hardware have fallen dramatically. Advances in consumer electronics have filtered into commercial aviation, like solid-state converters that can handle higher voltages, and monitoring systems make it possible to detect problems long before they become failures. For Boeing, designing the 787 from a clean sheet offered an opportunity. For the first time, their engineers would not be constrained by legacy layouts, existing ducting runs, or decades of incremental compromises. Instead, they could step back and ask, what would this aircraft look like if electricity and not bleed air became the primary way energy flowed from the engines to pretty much anything else? Well, each 787 engine is fitted with two massive generators mounted directly to the engine gearbox. Cleverly, these are both generators and motors that can be used to start the engine on the ground or in flight. And of course, each one is capable of producing a lot of power. So that means there's two generators per engine, which is really rare in the airliner world. And let us know in the comments below if you know of any other jets with more than one generator per engine. But in addition to the 4 generators in its 2 engines, the 787 has 2 more generators on its auxiliary power unit, or APU, which is right at the back of the fuselage. If a 787 runs all of its generators at full capacity, it would produce a whopping 1.4 megawatts of power, which is enough to power almost 500 homes. And the biggest change this enables is the totally new cabin control system. On the 787, air from the cabin is drawn in through dedicated inlets on the fuselage and compressed by massive electric air compressors, which raise the air pressure to produce a cabin altitude of around 6,000 or 7,000 feet before sending it through the familiar air conditioning packs, where temperature and humidity are controlled before the air enters the cabin. Wing ice protection follows the same philosophy. On most other airliners, bleed air is routed into the leading edges of the wings to keep ice from forming. On the 787 though, those leading edges are protected using electrical heating elements embedded within the structure, kind of like the ones you see in your car window to melt frost and snow on a cold winter's morning. This eliminates long runs of hot ducting through the wing and gives the system fine-grained control over exactly where and when the heat is applied, while also eliminating a source of maintenance headaches. And given the extra electrical power, Boeing also gave the 787 brakes that are powered electrically, not hydraulically, which is another first. However, none of this comes for free, of course. To make this architecture work, Boeing had to design an electrical system unlike anything that had ever been flown on a commercial airliner before. The 787 uses double the voltage of previous aircraft, going from 115 volts to 235. And they also added multiple layers of redundancy, extensive power conversion, and sophisticated control logic to manage the loads, prioritize essential systems, and shed non-critical ones if necessary. So this means that Boeing replaced miles of hot pneumatic ducting with miles of heavy electrical cabling, power electronics, and cooling systems for the electronics. The airplane effectively trades thermal complexity for electrical complexity, and one set of engineering challenges for another. But the payoff can be big. Boeing estimated that they could cut fuel burn by 2 to 3% compared to traditional bleed air systems, and they could do it while lowering maintenance cost and increasing dispatch reliability. That's because in addition to saving weight, electrical systems draw power only when they're commanded. They can be monitored continuously, adjusted dynamically, and integrated tightly with the aircraft's automation. And that's why Boeing decided to take this development risk. But soon after this, Airbus looked at the same problem when they developed their A350 and said, "Nah, we'll stick to bleed air, thanks." But why? Airbus didn't think the idea was unworkable, but instead they just concluded that at the aircraft level, the benefits simply didn't justify the cost and risk. Well, not yet. From Airbus's perspective, eliminating bleed air didn't remove energy extraction from the engines, it just changed the form. You weren't getting rid of the penalty, you were moving it somewhere else. Airbus engineers concluded that once you accounted for the weight of additional generators, power electronics, cooling systems, redundancy, and wiring, the overall efficiency gain of a bleedless architecture was modest at best. Real, yes, but too small to be worth the bother. And those gains had to be balanced against a very real increase in system complexity and development risk. The A350 program was already ambitious. Airbus was introducing an all-new composite fuselage, built using a more complex method than what Boeing were using in the composite fuselage of the 787. The A350 also had a new wing, new systems architecture, and the most powerful civil turbofan ever built at the time in the form of the Rolls-Royce Trent XWB. So piling a completely new electrical philosophy on top of all of that would have added another major unknown, with consequences for certification, schedule, and reliability. So instead, Airbus chose a more conservative path, but one they were confident in. So rather than eliminating bleed air, they just focused on making it better. The A350 retains a conventional bleed air architecture, but it's a totally clean sheet design that takes advantage of technical improvements and miniaturization of materials. They also eliminated the need for complex and expensive lithium-ion batteries, a necessity of the 787's bleedless design that caused so many headaches for Boeing when the jet was first introduced. At the same time, Airbus really embraced electrification, where it delivered the clearest benefit with the least risk. They simplified its hydraulic architecture, relying more heavily on electrically powered actuators for backup control and used electrical actuators in the hydraulic system. And these actuators are so powerful, in fact, that the A350's flight crew could control the plane even in the event of a total hydraulic loss. And by the time the A350 entered service, engine technology had advanced even further. The Trent XWB was optimized from the outset to work with the Airbus bleed air system, reducing inefficiencies so that the marginal penalty of bleed extraction made it even harder to justify redesigning the entire aircraft. From Airbus's perspective, the question wasn't whether bleedless aeroplanes could work. Boeing had already proven that. The question instead was whether it was the smartest place to spend engineering risk and program capital when similar aircraft level performance could be achieved in other ways. And in hindsight, that decision did pay off. The A350 entered service with fewer system level surprises, excellent dispatch reliability, and fuel burn that matched its competition. Airliners got an aircraft that delivered the promised efficiency gains without introducing a fundamentally new operational philosophy. Boeing and Airbus looked at the same technological moment and made opposite choices, and both were kind of right. The 787 proved that a largely bleedless architecture is indeed viable, efficient, and scalable. It pushed the industry forward and forced everyone to rethink assumptions that had gone unchallenged for decades. Whilst the A350 proved that you could achieve nearly the same end result without taking that leap by refining existing systems and electrifying selectively. However, is this awkward conclusion the final word of the story? Well, maybe not. More recently, Airbus has been working on solutions for micro-hybridization or electrification of aircraft systems for future aircraft designs. Some of this work is because such designs would make sense for aircraft that use alternative means of propulsion like hydrogen. But more broadly, this work's put more emphasis on developing even better, more efficient and lighter batteries and other electrical systems which would benefit conventional aircraft. So, one way or another, there's more to come from this story. Ultimately, the real legacy of the 787 isn't that it eliminated bleed air, it's that it made the industry ask whether it still deserved to be there at all. But what do you think? Will their next Airbus or Boeing aircraft use bleed air? Let us know in the comments below. I'm Ben Watts, you're watching Mentour now. Have an amazing week, and I'll see you next time.